Hello, my name is Ben Charbonneau, and this is part of 1.3, the counting circuit. Section 1, button input. The button input consists of 3 parts as listed in the parts table. When the PBNO is not pressed, the inputs are high, until the PBNO is pressed, pulling them to ground. In a pull-up resistor configuration, the resistor connects the PBNO to power. In a pull-down resistor configuration, the resistor connects the PBNO to ground. This circuit uses the pull-up configuration. Section 2, NAND gate oscillator. This circuit consists of 7 additional parts. This circuit uses a 411 NAND gate that produces a high output unless both inputs are high. NAND gate oscillators are circuits that generate repeating square wave signals by utilizing NAND gates in feedback loops, which produce oscillations through the use of a clock signal. Clock signals are periodic electrical square waves that oscillate from high and low. The duration of the oscillations are controlled by RC network 1, and RC network 2 controls the frequency of them. The oscillations of the NGO are used as clock signal for the rest of the counting circuit. Section 3, the decade counter. The decade counter consists of 3 new parts as seen in the parts table. The decade counter is a circuit that counts from 0 to 9 and displays the counting on 10 individual displays on an LED bar graph. The clock signal of the 417 chip is the output of the NAND gate oscillator. Each rise in the clock signal indicates a clock pulse to advance the count. This happens until the clock signal rolls over back to 0 and continues until the clock signal stops and the count becomes static. Section 4, the decimal counting binary up-down counter. This circuit consists of 5 new parts as seen in the parts table. This circuit uses a 4516 since it counts from 0 to 15, but the final counting circuit uses a 4510, which counts from 0 to 9. It introduces an up-down count. When the slide switch is wired high, it counts up, and when it's wired low, it counts down. The reset button is connected to the reset pin of the 4516, and when pressed, it resets the count. This circuit is a 4-bit counter with 4 LEDs to show the counting advancements, each representing a different bit. The 5th and 6th sections of the counting circuit are the binary counting decimal decoder, which has parts table as seen on screen, and the 7-segment display, which has parts table seen on screen. To make the final breadboard prototype, the 4511 processes BCD input data, decoding the signal combinations, and then deciding which segments the 7-segment display should light up to represent the right number. The 7-segment display is used to visualize the numbers. It consists of 7 arranged LEDs in a digit pattern. The prototype that we use uses the common cathode variation, in which cathode pins of the LED segments are connected to a common ground pin. For the segment to light up, its corresponding pin needs to receive a high signal. Section 7, the counting circuit PCB. The PCB requires 6 new components, as well as chips, resistors, and switches, as shown on the PCB. Once a PCB is soldered, the PCB is completed, and the case is needed to finish the build, along with providing power to it. Step 8. The final step of the single-digit counting circuit is the case, in which the PCB is screwed into, completing the final build. 3 additional components are required to complete the case. This concludes Project 1.3, the counting circuit. Thank you for listening.